Hello students, welcome to Sources classes. In this video I am solving Isi M.Math 2020 subjective paper from question number 3. This is the part 2. So this says that let f the real plane is twice continuous differentiable function, so that f of x plus h plus f of x minus h minus 2fx h square is f double dash x, and also show that for other part. So let me just start with the first part. So we need to use the Taylor's expansion for this. So using Taylor's expansion of f with a remainder in the integral form. So we know that x of x plus h is fx plus, in the very beginning of the question, to judge that on which pathway you will proceed. F of x plus h, f double dash y, f of x plus h minus y dy. So now then f of x plus h, now the main calculation comes in, this whole thing, minus 2fx h square. Okay, so 1 by h square fx, h into f dash x we are replacing, and x plus h, f double dash y, x plus h minus y and dy, plus this fx minus h f dash x and x to x minus h, f double dash y, x minus h minus y dy minus 2 of fx. So this whole thing is 1 by h square comes down to x to x plus h, f double dash y, x plus h minus y dy by 1 by h square. The limit is x to x minus h, f double dash y, x minus h minus y dy. Okay. So now 1 by h square, x to x plus h, f double dash y, f double dash x, x plus h minus y dy, 1 by h square, x to x minus h, f double dash y, f double dash x, and this will be multiplied by x minus h minus y. Dy plus f double dash x. So we use the continuity of the second derivative. So given epsilon greater than 0, there exists sigma greater than 0 such that z minus x then equal to this. So f double dash z minus f double dash x, taking modulus obviously, has to be less than equal to. So now if h, let mod h less than equal to sigma. So f of x plus h here plus f of x minus h minus 2fx by h square minus f double dash x, this thing has to be less than equal to 1 by h square, x to x plus h, f double dash y, and this will be the difference from this part, and plus 1 by h square outside. So x to x minus h, f double dash y minus f double dash x, x minus h minus y dy. So this thing. Now since x plus h minus y less than equal to mod h, and x minus h minus y less than equal to mod h, these two things less than equal to 2h square x to x plus mod h, then this is epsilon h and dy, so this is equal to this. So the convergence limit h tends to 0, f of x plus h plus f of x minus h minus 2 into fx by h square is nothing but f double dash x according to this. So the value is being done. So this is proved. Next, now time for part B. In part B, they are asking, if you remember, so they were been asking, the part B was the show that the f further satisfies 1 by 2y x minus y x plus y f t dt, that is equal to fx. Okay, such that fx equal to ax plus b. Under these circumstances, differentiate the identity. Let's do it. 1 by 2y x minus, so this is the identity, so with respect to y, so this is x plus y plus f of x minus y by 2y, 1 by 2y square x minus y x plus y ft dt equal to 0. So it follows that f of x plus y x minus y equal to 1 by y x minus y to x plus y ft dt, so that is equal to 2 into fx, and this thing will be equal to 0. So letting y tends to 0, we deduce that f double dash x will be equal to 0. So fx obviously equal to ax plus b. That's it. Hence the final answer. Now we proceed to the next question, that is question number 4. So 4 says it's a twice differentiable continuous function, so that f is bounded, f double dash x is positive, then f must be a constant. This one is an easy one. By assumption, the derivative of f is increasing. If we take increasing, assume that there exists x0 in this interval, so here, so for f dash x0 if we take, so that is also positive as x greater than x0. So fx equal to f of x0 x f dash y dy, this is also greater than equal to f of x0 plus x0 to x2 f dash x0 dy. So now here if we just put the values, f dash x0, so this tends to infinity as x tends to infinity. Okay, so now here this statement, this one contradicts the fact that f is bounded, that is given here. So assume that there exists x0 in R such that f dash x0 is negative. So that time we have taken positive, this time we will be taking negative. So x is actually less than x0, so this time fx equal to f of x0 minus x to x0 f dash y dy greater than equal to f of x0 minus x to x0 f dash x0 dy. So that is f of x0 plus x minus x0 f dash x0. So this tends to infinity as x tends to 0. So these two are done. So again it contradicts the fact that f is bounded. So in both way it is not being done. So we deduce that the only possibility is f dash x is equal to 0. So I greater than contradicts, and so that is f is a constant. So both are proved.